This lecture will be on paint. Paint, of course, is everywhere. You know, all kinds of surfaces are painted, and violent crimes of entry, that is, burglaries and so forth, in which they pry open doors and pry open windows. They certainly leave paint on the tool that they use, and they leave paint from the tool on the surface which they disturb. So we get a fair number of paint samples from commercial and residential buildings, but the majority of the paint samples that come into the crime laboratory are automobile paints, primarily from things like hit and runs and situations where paint is transferred from one car to another, or from a car to a surface, or from a car to a victim which is hit by the car. So we'll spend a little bit of time talking about commercial paints, but we'll spend most of our time talking about automobile paints. And we need to talk about the analytical techniques for paint comparisons. Typically, if you don't have a sample to compare, paint examinations don't yield much information. The first thing to assess in the examination of a paint sample is the obvious one, which is color. We are pretty good at distinguishing color with our eyes. So the first process I will illustrate with a slide. This is a picture of a microscope slide. The wide black line in the middle separates the paint from the crime scene on the right, and the paint from and is just compare them side by side to determine if the colors are similar or indistinguishable, and also to examine the layers. In a regular automobile paint sample, there are 4 or 5 layers, starting with the base primer coat, then the upper primer coat, then the color coat or main layer, followed by a clear coat. The sequence must be the same on both samples. The approximate width of each layer needs to correspond, and the colors need to be indistinguishable. The more layers you have, the more discriminating the examination will be. Normally that is a relatively quick and inexpensive examination, and it's a great place to start, because if you can eliminate the samples at that level, then you don't need to consider going on with more expensive analytical analyses. Enough layers, then it's actually possible to individualize. We had a rock in San Jose when I worked there, up on a hill, and it was regularly painted by the local high schools. Whenever they had an athletic event and one team emerged victorious, they would drive up to that rock and paint it their color. And over the years, it had many layers. Someone went up in the area and vandalized it, and they got a suspect truck which had a chip of paint on it with 23 layers, and all in the same sequence as on the rock. We concluded that there was undoubtedly not another rock in the world that would have had that many layers of paint in that sequence. So it was deemed that the suspect truck was the one that had done the damage. But that's a highly unusual situation. Usually you have, as I said, 4 or 5 layers. Maybe in a case where a vehicle has been repainted, you may have a few more, but usually that's just a good starting point. And then the next test that is usually conducted is one of a chemical solvent test. We take a spot plate, which is a ceramic plate that has depressions in it, and you place a tiny chip of paint in each of the depressions side by side for about 5 or 6, depending on how many chemicals you're going to use. And then you take various solvents, usually including sulfuric acid, acetone, sodium hydroxide, and whatever others the analyst decides to use. And then you drop a drop of each of the solvents on each of a pair of paint chips and watch the results. Sometimes nothing happens. Sometimes the paint curls up. Sometimes it dissolves. Sometimes it changes color. But if the 2 chips do something different, one rolls up in a ball and the other one does nothing, then you can conclude that they're not the same kind of paint. Now, none of these analytical techniques attempts to identify the chemical makeup of the paint. It's really not important. What's important is, are they the same? And so it's okay if we don't know why the paint changed colors. For example, it's only important that they change the same color. If they don't, then that's the end of the examination. We don't need to go any further. They're not from the same source. So the next analytical technique depends on the laboratory's capabilities. We've talked about gas chromatography, and you can imagine that gas chromatography is not possible with paint, because paint is not a gas. So you could dissolve it in a solvent, but that's oftentimes not a practical solution. So some gas chromatographs have on the front end what is called a pyrolyzer. It's essentially just an oven. You inject into that oven, and then you turn on the electricity, and it almost instantly vaporizes the paint. And in the process of vaporizing it, a number of what we call pyrolysis products are formed, and they are then introduced into the gas chromatograph. Turns out there may be a very large number, 20 or 30 sometimes, components, pyrolysis components of a paint sample. And so if you do these tests, one on the standard and one on the question sample, and they're the same, that's a very powerful indication that they are in fact similar and could have come from the same kind of car. Another analytical test which is commonly used is infrared spectrophotometry. And again, we've talked about that earlier on, so we don't need to go over that again, but just suffice it to say that we have to grind up the paint and mount it in the instrument such that the light passes through it, and that generates an infrared spectrum. And we compare the peaks, and the peaks, if they're the same paint, the peaks need to be the same, need to be in the same wavelengths and the same relative intensities. So then when we're done with that, then we're pretty sure we know whether the paints are the same or whether they have significant differences. The problem is, what does that mean? Does that mean that the paints came from the same car, or does that mean they came from the same batch of paint, that was painted in the factory? So, or does that mean it's simply, General Motors car, for example? And a few studies have been done to give us some ideas of what probabilities exist out there. One well-known study that is cited in your book was conducted by the Center for Forensic Science in Toronto, Canada, which is one of the leading crime laboratories in the world. They went to a wrecking yard, which we call a junkyard, and sampled 260 vehicles, took paint from 260 different vehicles, then subjected them to the test we've been mentioning. They didn't use pyrolysis GC, but they did use microscopic comparisons, and they were able to distinguish all but two of the pairs of paint. Mathematically, that works out to be the odds of finding two randomly selected paint samples that match is about 1 in 33,000. I don't think I've ever used that number in my testimony. I've merely said that the two paint samples are similar and could have come from the same car. We did a few studies back in the day when we looked at colors and so forth, and so I can add a little bit to that and say, well, this is a color that's not particularly common in our environment right now, or this is a common color. White, of course, is the most common color, but there are lots of shades of white as well. So I've testified in a number of hit-and-run type situations, and over the years, if I've said that the two paint chips were indistinguishable, it's resulted in a conviction, and if I have reported that they did not match, then that's resulted in a dismissal of the case. So it's a very powerful evidence. It's easily collected. A few things you need to remember, of course, are that you need to take the samples, the control samples, from very near the area of damage. And I think back in the day, back when we were still lecturing, I mentioned a case in which they took the control sample from a door of a car, and I was comparing that to the paint from a bumper, and they weren't the same. They weren't the same kind of paint, and so you need to make sure that the control sample is taken from the area of damage. You also need to examine the relationships of the cars to see that the damage corresponds to the area of the damage on the victim vehicle. So if it's up on the 2 feet up on the victim car, it ought to be 2 feet up on the suspect car as well, for example. And then other considerations that are discovered by the detectives investigating the case also come into play, as always. But paint is a good type of physical evidence. You need to make sure that when you collect the control that you get all of the layers. So that means usually scraping with a scalpel. And normally what I do is just hold a paper underneath the blade as I'm scraping, and then fold it up into a bindle or let it go down into a small vial, and make sure I've got about a sample the size of a dime is certainly adequate, or maybe even a little bit smaller than that. But you've got all the layers, and you've got the sample taken from the appropriate area of the car, and it's easily preserved. You don't have to worry about too hot or too cold. You don't need to freeze it or refrigerate it, or worry about getting it decomposed from the elements. So that will conclude my discussion on paint examination, and we'll move on to the next subject, which is glass. Glass is a very common type of physical evidence found at crime scenes. It's involved in lots of burglaries and lots of vandalisms, automobile accidents, where you have automobile glass, headlight glass, etc. So glass is an interesting material. Usually we think of solids and liquids and gases as the three basic forms of matter. Glass doesn't nicely fit in any one of those three. I'm sure you think glass is a solid, but it's actually a very, very, very viscous liquid. That is, if you have a pane of glass that's been in a window for 30 or 40 or 50 years, if you measure the thickness at the top versus the thickness at the bottom, you'll find that it's much thicker at the bottom because it gradually flows from the top to the bottom by gravity. Physicists, astrophysicists are fond of saying gravity always wins, and in the case of glass, it's true. Given enough time, glass will succumb to gravity and will flow. But the rate of flowing is very, very, very slow. So we call it a vitreous material. Glass is made by melting sand. Depending on the type of sand, usually it's basically what we call silica sand. But there's other kinds of sand that result in different kinds of glass for different purposes. But it melts at very high temperature. So you put it in an oven and heat it up, and when it melts, then you cool it down very rapidly. And so then the molecules don't have an opportunity to arrange themselves in their normal crystalline structure. The normal arrangement of molecules in solids is in crystal structure, which means they have fairly precise shapes and angles. When they cool quickly, they don't have an opportunity to arrange that way, and so glass does not have that rigid crystalline structure. The molecules are more or less jumbled together, which is probably not a good word, but that's a word that we understand. In any event, so glass is pretty simple in its composition, and pretty simple to make as long as you've got an oven that'll heat it up sufficiently and some kind of a pot that won't melt at that temperature. And they don't stir it up. They just heat it up, and then depending on what they're going to use it for, then they pour it out of the vat in various reasons. If they're going to make it like a window glass or what we call flat glass, they will pour it out on a bed of molten tin, and that tin is smooth, and so as the glass cools on the molten tin, it cools without any impurities or obstructions or variations to the surface, and that allows for good transmission of light. You don't get all kinds of weird reflections and so forth in the glass. It also imparts to the side that has been in contact with the tin, it oftentimes allows it to have a different colored fluorescence under UV light. And so that's one of the things that we do when we look at a piece of flat glass is we shine a UV light on it. And sometimes it'll fluoresce yellow and sometimes a pale green. And it won't fluoresce on the other side. So then you know that, okay, this is a piece of what we call float glass. They call it float because it floats on the tin. So if you want to do a comparison of glass, usually the basic components are not very discriminating. If it's the most common kind of glass, which is soda lime glass, then the basic elements present are pretty much present in any common glassware. And the differences between glass from one source and another source are their minor impurities, the things that are incidentally or accidentally incorporated into the glass as it's being manufactured in very, very small quantities. So you need a powerful instrument to measure those. There are a couple of laboratory tests that don't require an expensive instrument, and those are physical properties of glass, which do show variation over a relatively large area. And those two properties are density and refractive index. Density, if you remember your junior high school science classes, density is mass per volume, or we usually think of weight per volume, but the difference between weight and mass on the surface of the earth is negligible. So we can weigh things and we get weight per volume. The nice thing about density is that you can compare two samples that are not the same exact size or shape, because it's a ratio. So the ratio of weight per volume increases as you have more weight, but it also increases as you have more volume. So if you have a piece of glass that's about the same size and shape, you can compare the density. And density is one of the really common measuring properties of glass. There's a number of ways you can compare density. I prefer the float sink method, at least to start with, which is you take a test tube or a long tube, usually longer than an ordinary test tube, and you put some liquid in it that's very heavy, bromoform, which has a very high density, and most glass floats in bromoform. So if you drop a solid into a liquid, then if the solid has the same density as the liquid, the object will suspend itself in the liquid. It won't float, it won't sink, it will just stay pretty much in the liquid. If the density of the liquid is greater than the density of the glass, then the glass will float on top. If the density of the glass is greater than that of the liquid, it will sink. So what you do is you take the bromoform, and to the bromoform you add a little bit of a less dense liquid, such as bromobenzene, which has a density less than most glass. And then you drop the glass in there, and if it floats, then you know the densities of the liquid is too high, and so you add a little more bromobenzene. And if it's too low, you add a little more bromoform, and you just keep doing that until you get it so that the glass just barely floats on the top. It looks like it might sink, but it doesn't. Then you drop the other piece in there, and if it sinks, then the game is over. You don't. They're different. But if they both float, then you can very gently warm up the liquid, and of course warming it up will reduce the density of the liquid, and it will reduce it much faster than it reduces the density of the glass. So at some point, as the liquid warms up and the density of the liquid decreases, at some point the density of the liquid will be less than the density of the glass, and the glass will begin to sink. If you do it right, if you're really careful, you can just hold the tube in your hand, and the warmth of your hand will cause the liquid to warm up enough that they'll sink. And they need to sink both at the same rate if they're from the same source. If one sinks before the other, then you can say, well, the densities are different, and so they didn't come from the same glass or the same window pane or the same container, whatever container it was. That's called the float sink method, and it's a little bit tedious and a little bit tricky, but it's quite a fun little technique once you get it going. Another technique is another physical property is refractive index. It turns out that when glass or any transparent material has light strike it, the light can either reflect, or it can be absorbed, or it can transmit through. If it transmits through, then that's called refraction. And what happens is that when the light comes out, it's going at a slightly different speed than when it entered, and that results in the light being bent. So this is a phenomenon that you see a lot, but you don't really pay much attention to it. As an example, if you see something in a river or a lake down on the bottom, and you reach down to where you think it is, it won't be exactly where you think it is, and that's because the light coming out of the water is bent. And so then if you're reaching down under the water, you need to usually reach a little bit lower than what your eye tells you, because your brain doesn't compensate for that bending. Well, the refractive index is an index that measures the amount of bending, and glass is very sensitive to refractive index. Different glasses have different refractive indices. There's a chart in your book, which I will show you, that demonstrates the FBI's record keeping of refractive indices of glass. This is a photograph of a chart taken from your book. It is a graph of about 2,000 glass samples which were received in the FBI laboratory, and their refractive index was determined. If you look at it carefully, you will see that even the most common of the glass samples was only, the refractive index was only in about 100 or 110 out of the 2,000, and most of the samples were far fewer than that. So if you get a refractive index that is a rare refractive index, of course that gives you a better discrimination than if you get the common ones. But even the common ones, you get a pretty good discrimination factor. And if two pieces of glass have the same refractive index, then there's a pretty strong likelihood that they have a common origin. We typically used to do both density and refractive index numbers, but it was determined a few years ago that refractive index and density are not independent variables, so now most laboratories either do one or the other. In the meantime, a laboratory in England learned how to make an instrument that measures refractive index. It's called a GRIM, G-R-I-M, and it's spoken of in your chapter, so you should read that section of the book and find out about the GRIM, which is an automated technique for determining refractive index. So the laboratory examination of glass basically starts with the visual examination of the glass. Maybe you can determine from that whether it has a flat surface like a window, or whether it's completely irregular in shape, as though it were broken from a bottle or that sort of thing. You can check the fluorescence under UV light and check the color of the glass itself. So these are just visual comparisons. And then you can do refractive index and or density. And if you have the proper instrumentation for determining inorganic trace elements, then that can be done, which adds to the likelihood of telling two non-common source pieces of glass apart. When you're done with all of those analyses, then general thinking is that if two pieces of glass are indistinguishable by those techniques, that somewhere in the 90% range of odds that they are from the same window or the same object. And maybe some experts would go a little bit lower, maybe some a little bit higher, but somewhere in that range. I've had a number of interesting glass cases. We had a couple of younger men who decided they wanted to break windows in the business district of Logan, and they broke several windows, and they were subsequently caught, and they had a baseball bat in their possession, a wooden baseball bat, and there was lots of glass in the wood, and they brought me some samples from the broken windows, and I was able to match up some of them to the pieces of glass embedded in the wood of the baseball bat. So glass, it's always worth looking for. If you go into a home or a residence or a business where there's broken glass, obviously you want to collect some of the glass immediately. And if there's large pieces, then keep them intact. But then if you subsequently get a suspect, you want to check his clothing and his, in particular, his shoes for the presence of pieces of glass, because if he's stepped in the glass, some of it might be embedded in the soles of his shoes. And we sent a couple of our students down to check out the likelihood of glass being in shoes. And so they would just went downtown Ogden and on a busy street corner, and when someone would come by, they'd say, we're students from Weaver State, and we're doing a little survey. Would you mind if we looked at the bottom of your shoes? And most people would say, yeah, go ahead. Other people weren't so friendly. But anyway, they found that it's pretty unlikely to have a piece of glass in your shoe. So just finding glass in your shoe is somewhat incriminating. And then certainly if the glass matches the suspect glass, then there's a pretty good chance that that you can get a conviction. We had a guy that was found on the inside of a the Desert Industries, and it used to be on Washington Boulevard in downtown Ogden. And I will show you the glass from that. This is a picture of the boot taken from the suspect that was found inside the building. This shows a piece of glass that was embedded in his boot. And the next picture shows inside the boot. You can see the glass penetrated his boot and was inside. So they found this guy walking around inside the Desert Industries late at night. Front window had been broken, and they asked him what he was doing in there, and he said he was shopping. And they said, well, didn't you notice that it was closed? And he said, no. And then he said, I've got something wrong with my leg. So they had him sit down, and they pulled off his boot, and it was full of blood. And so they looked inside, and there was a piece of glass. So they brought me the boot and some glass from the window that had been broken out of the Desert Industries, and I compared them, and they matched in all the characteristics that I used. And not that it wasn't obvious that he was the guy, but now it was, we had some physical evidence. But I think about that often, and I think, what kind of person burglarizes the DI? Kind of what you might call a down and outer, or maybe something a little stronger than that. But I think that's that's certainly not a high roller burglar. In addition to making comparisons of glass particles, there are some other examinations that we can make. Glass being very stiff, if it has been shot at or penetrated by something that makes a hole in it, we can determine the general type of object that was used. If it's a bullet, fast-moving object, the bullet or fast-moving object will push a wedge out of the glass so that the entrance side of the hole will be smaller than the exit side of the hole. So you can tell whether the bullet was, which way the bullet was coming through the glass. If it's a slow-moving object like a rock or a brick or something like that, then it will make a spider web type fracture with lines radiating out from the center, and then connecting those with circular fractures. I'll show you pictures to demonstrate that. So these pictures show what I talked about earlier, the wedge shape pushed out by a fast-moving object like a bullet. This one shows the slow-moving object, and you'll notice on the left where it says force that the brick or rock or whatever hits the glass and pushes it to the right. The stiffness of the glass causes a second break to occur up above, labeled A, and you can see that opens in the opposite direction. Interestingly enough, that results in our ability to determine whether glass was broken from the inside or the outside. Not a particularly common question, but one that can be answered, and I will show you that. This is a photograph of a broken piece of glass. This is the edge of the glass, and you can see those dark curved lines in the glass, which are called stress marks, and they occur as a result of the stress when the glass is fractured. They will occur on glass that is broken in the manner we talked about, with a slower moving object, and the result being the spiderweb spiderweb looking fracture pattern. So if you examine the broken edge of the glass, if you know whether it's a radiating fracture or a concentric fracture, then you can determine if it was broken from the inside or the outside. In this picture, the force would have come from the right to the left. There are, of course, exceptions to this procedure. It must be a slow-moving object, not a fast-moving object, and it must not be as a result of a heat, or if the glass is flat up against another hard surface, like if the glass is lying on the floor, or if it is anything other than plain flat glass, which doesn't occur in vehicles. Vehicle glass is different than flat glass, normal flat glass. There are two kinds of automobile glasses. One is the type that is present in the windshield of cars in the United States. By law, they must be what is called laminated glass, which is a pane of glass and a layer of plastic, and then another pane of glass. So in those kinds of glasses, there is not the same kind of fracturing. It is designed to break in a less dangerous way, so that you don't have shards of pointed glass that can injure persons in an accident. The rest of the windows in most cars in the United States are made of what is called tempered glass, and that is glass that is produced under constant pressure, and when they fracture into lots and lots of irregular shaped cracks, again removing the possibility of sharp spear-like points that could cause serious damage if a person's body or parts thereof were thrust through the window. So tempered glass and laminated glass, and glass broken as a result of heat, or glass that is supported by something flat up against it, like another wall or a floor, will not exhibit stress marks. So that's one thing to look for if you are examining a fire and there are broken windows in the house. You should examine the edges of the window fragments to see if they have stress marks. If they do, that it would indicate that the fractures were not created by the fire, but perhaps by a burglar who entered and then started the fire to cover up his nefarious deed. If you anticipate that direction of force might be an issue, you should be careful to label some of the pieces of glass front and back, and the best ones are ones that still remain in the window pane, because you can tell whether they're inside or outside. If you don't label them, then knowing which direction the force came from won't help you if you don't know which is front and which is back. But in any event, that's brings up the point of collection and preservation of glass. Glass, of course, is easily preserved, as is most of the things we've been talking about recently. It's a matter of making sure you collect sufficient sample for control. If you go to a crime and there's broken windows or broken glass, be sure to collect and preserve most of the larger pieces. The best possible match for glass is done with what we call the physical match earlier on, where you fit the pieces together like a jigsaw puzzle, and that requires that you have most of the fragments and that they remain unbroken. So collect them in such a way that you don't cause further damage to the larger pieces. Collect a good representative sample and in the case of wanting to make a physical match, collect all of them, and then you can maybe reconstruct the window or the bottle or whatever the glass was originally. So if you have a suspect that you suspect may have stepped in or been close to the glass, you should make sure you collect their clothing, and it's recommended that you have them stand on a piece of white butcher paper or larger paper, so that as they take off their clothes, if any glass is inadvertently shaken off their clothing, it will remain in the glass that's on the floor, and you can just fold that up and keep it. Pay particular attention to the shoes, because they're a place where glass is often found. Interestingly enough, when a large pane of glass is broken by a brick or a rock, a good amount of glass comes back in the direction of the thrower. So if you were to stand 6 or 8 feet away from a window and throw a rock through it, there's a strong likelihood that glass will fly back and get and come in contact with you and maybe get entangled in your clothes or in your hair. I don't have to worry about that. But any event, we have to think about that there's a possibility of glass on their clothes, even if they were standing outside the window and broke it with a large object or a slow-moving object. So now we want to turn our attention to another piece of trace evidence. In your book, there's a photograph of a lamp filament. I want to talk a little bit about that lamp filament and what the importance of it is. Occasionally a situation arises where it's important to know whether a light was on or off at the time the bulb was broken. I will proceed to show you that that is possible. You need to be using a lamp that has a tungsten filament, which most of our incandescent lamps have. That is a little spring-shaped, coiled-shaped wire that is heated as the electricity passes through it, and at a certain temperature, somewhere around 1,000 degrees, it gives out light. It turns out that the reason that it works is because the bulb is a vacuum. The air has been evacuated from the bulb, and so the filament, when it gets hot, doesn't burn up. If you were to pass that electricity through the filament in the presence of oxygen, it would quickly oxidize, and and it would be burnt through. Here are some pictures. This is a picture of several lamp filaments that have been exposed to heat and in the presence of oxygen. The first one on the left was not heated. The second one, the yellow one, was heated to 700 degrees, and you can see that it's changed color. And the succeeding ones from that yellow one to the right each received more heat, and the result was that they changed colors. So the oxidation results in a change of color. It also might result in some other changes, which I will show. This shows a lamp that has two filaments, as you might see in an automobile headlight with the high beam and low beam. You can see the top filament is intact and looks normal. The bottom one is very distorted, and that is because when it was broken, the filament was hot and so easily bent and misshapen. That is another common thing that happens in addition to the change in color. A third thing that can happen is that small pieces of the glass can strike the filament and become melted onto it. Here's an example of that with the upper filament not being hot, lower filament hot, and having glass stuck to it. An example of a case in which this was used: a young lady was driving down Harrison Boulevard in Ogden City when a man turned left in front of her, and she crashed into the car, and damage was done to both vehicles. When the policeman arrived, he interviewed the driver of the left turner, who said the reason he turned left was because her lights were not on and he didn't see her coming. When he interviewed the young lady, she was very distraught and just wasn't able to give him a good statement. The next day, though, she called him and said, I'm quite positive my lights were on. So the officer, who had been trained at Weber State, fortunately went to the car and removed the filament from the girl's headlight, brought it up to me, and it was clear that the light had been on when the impact occurred. So he went back and gave the ticket to the left-hand turner, and the girl was absolved of any wrongdoing. So that doesn't happen every day, but it's, when you have an examination that you can use, then eventually in your career you'll probably have a chance to use it. That's been my experience. It is, of course, that very important that you retrieve the filament. If it is still attached to the bulb, bring the entire bulb. If not, then bring the remains of the bulb and filament if you can find it. We can't do the examination without the filament. The last section in this chapter is soil. Soil is just a fancy word for dirt, and of course dirt can have many components. Virtually anything can be in dirt, from inorganic to organic to man-made. So the possibilities for comparison are virtually endless. Unfortunately, most criminalists are not trained in geology and therefore are not able to take full advantage of identifying the minerals that are present. But relatively simple examinations can prove quite discriminating. As you may have noticed, if you have completed the assignment on soil, many of the students who complete that assignment are quite surprised at the differences in the even just the color of soil over a relatively short distance. So the first thing that we do is compare the soils side by side. The best light you can use is if you have a non-sunlit window, a north-facing window, and use ordinary daylight. The sample should be placed on a white background and then on a black background, because you'll get different appearances with different backgrounds. If the soils are noticeably different in color, then you would have to say they don't match. The next thing to do would be to gently dampen them, not so they're wet and muddy, but just so they're damp. Most soils will change color. Most of them probably turn darker, but sometimes one turns color and the other one doesn't, so you've separated them on that basis. The next thing to do is to determine the particle size. You can purchase a set of screens. I had some nice round screens about that big around that differed in the size of the mesh from a quite a small mesh down to a very, very fine mesh. So I would arrange them with the larger meshes on the top and the finer mesh on the bottom. Then I would weigh a sample of the soil. If you have enough to weigh out 10 grams, that's a good sample size. Oftentimes you don't have enough of a sample for that, so maybe if there's not enough to take up space in the screens, then you probably can't do the test. But if you can weigh out 10 grams of each sample, gently break up the little clods of dirt, not forcefully. You don't want to break the little rocks apart, but so you don't grind them. You just kind of break them apart, and then dump the 110 gram sample in the top of the screen. And if you have a shaker in your lab, which that's all it does, is you put things on it and it shakes them and mixes them up. If you have a shaker, you should put the screens on a shaker. If not, you should try to gently shake them yourself, and then for the other sample, try to reproduce the shaking motion, same shake, number of shakes, and so forth. While the sample is on a large piece of white paper. Once you've completed the screening, you should weigh the samples in each screen and weigh the paper. So what you will have is different weights for different screens, so that each screen will have a minimum hole size, and particles larger than that won't go through. So if the first screen has 2 grams in it, then 20% of them are larger than that screen. You do that for each screen, and you end up with a sample size that can be compared. And if they're from the same place, the relative percentages will be very, very close. After you've done that, then you should do a stereoscopic examination under the dissecting microscope of each sample, noting any vegetative materials or man-made materials or organic materials, and then separating out the small pebbles. If you have some experience in geology and can identify the minerals, that's a plus. If you don't, then you just look at them with the stereoscopic microscope and see if they're the same color and represent approximately the same percentage of pebbles as the other samples. This examination, although it seems relatively simplistic, is quite discriminating. Once again, the Canadians have done what is probably the best examination or testing of soils, and they did a study up in the Eastern Canadian area, in which they determined that if 2 soil samples were indistinguishable, the odds were 94 or 96. I have to look it up. Anyway, the odds were very high that they came from within 50 meters of each other. And I think that's probably the study that most criminalists look at to arrive at their decisions. Soil, of course, is not the same in Utah as it is in Canada, so may not be completely applicable, but gives you a good basis for comparison. When you are collecting soils, a few things that you need to keep in mind. First is that the samples may vary from closely associated places. I had a case in which a soil sample taken from one side of a vehicle was measurably different from a soil sample taken from the other side of the vehicle, and as you progressed down the road, it was a dirt road, down the road 40 or 50 feet, it changed again. So you need to make sure you have representative samples, not just one, but numerous samples. If they're wet, they need to be dried. But when you collect them, you try not to put them in plastic bags, because if you put them in plastic bags, the moisture will not evaporate, and things will begin to grow. You'll have mold and who knows what else, seeds might germinate. So if you have to collect them in a plastic bag because they're wet, then as soon as you get back to the lab, take them out and air dry them, and then package them in paper. If they're dry, package them in paper to start with, and collect a good representative sample, a half a cup or so as your standards from various places. Soil can be found on clothing, can be found on shoes, can be found on tires, and examinations can be made on all of those. If you take samples from a car that's been driven down a dirt or muddy dirt road, then you'll have numerous layers of dirt that have built up under the wheel wells. So try to get a sample of that and keep it intact so that you can see the various layers. So break off a chunk that includes the whole gamut of layers, and preserve that, and don't let it get broken up, and then you can subsequently separate those layers in the laboratory for additional comparisons. Soil, again, is one of those commonly overlooked samples. We need to think about them out in the field, and collect them and carefully document them and photograph them, as with all other kinds of evidence. There have been some studies to determine if we could use soil samples to help us identify the area from which the soil came. That normally is very difficult, but there may be situations in which you could narrow it down. If, for example, you were to find seeds or plants that grow in a particular area, then that would help lead you to that area. Or if you find a body and on that body you have soil or dirt that's inconsistent with where the body was found, then that would help you to recognize that the body was not did not die in that place, but was killed somewhere else and brought to some place and dumped off. So occasionally you can that can be helpful, and there are criminalists that specialize in pollen grain identification, which pollen is quite ubiquitous. It's everywhere, and so a good palynologist can sometimes tell you, well, this pollen is from such and such a plant, which we can say, well, that plant only grows up at the high elevations, or that plant only grows out in alkaline, marshy type areas, et cetera, et cetera. So that's a possibility as well. And if you have a palynologist in the area, and that's good investigators know those connections and can contact experts in the field in your particular area.